Okay, hello and welcome back. So we'll continue in our second week course that we are in the week 2, and if you remember from the previous module, we have been looking at the waste properties. So we looked at the moisture content, density, and some other physical properties of a certain waste stream. So we'll continue looking at some of the other physical properties, and we'll do some solve some example problems. I have some example problems as well, like how I have been telling you in the if you have and I hope you should have gone through the previous module. I have been stressing on the fact that this mass and density, they are related, and how the data collected related to mass or density is applied. So we'll see some of the example problems in how it is being done, just to reinforce those ideas. So let's get started. So if you remember, in the previous module we were talking about the mass, volume, density, specific gravity, moisture content. So now we'll kind of continue that, and another property, another important property is what is known as the porosity. So porosity, I'm pretty sure if you have looked at porosity earlier in a soil mechanics course or any in your high school science classes as well, porosity as we define it, as you can see on this particular slide, it's a very simple way of defining the porosity. It's essentially volume of voids divided by the total volume. So porosity is whatever is the volume in the void. So if you have, say, if you have several pebbles all put together, so if depending on the size of the pebbles, you can see that when they are stacked together, in between we have some space left. So these are the space in the middle. So these are the void spaces. These are what we call the void space. So these void space, so volume of these void spaces divided by, so that's the volume of those void spaces divided by the total volume. So if you take at the total of this, so the total volume is what is in the denominator, and the volume of these void spaces is in the numerator. So that gives us the void, the porosity. Why it is important? Remember, when we're talking about the landfill design, if there is a porosity will have soil air will be trapped there. So in case, if you remember from the previous discussion we had, that when the waste degrades, methane is produced. So now this methane, if for some reason in the hot and humid kind of weather, very high temperature, waste degradation is an exothermic process as well, which releases the heat. So if the temperature goes up, methane being a flammable gas, it does catch fire if the conditions are suitable. And in that case, if you have a big void spaces, that means you have air pockets, and then air pockets means it has oxygen. So if oxygen is present, methane is burning, so the fire can propagate into the landfill. So that's another reason why we do the compaction on the landfill. If you saw those pictures where we showed you that several compactors are used to compact the garbage. Reason for that is, of course, one of the reason is to increase the strength, the stability of the landfill, so that our shear, that the CN5 values are good. CN5 from the soil mechanics are good enough, and then the structure is strong, it will not collapse. But at the same time, it gets rid of these void spaces. These void spaces will be gone. And these void spaces, because when you compact it from the top, say if you are applying pressure from the top, these void spaces will disappear, and then these things will get compressed. And in that case, what you will have is there is a lack of oxygen. So if there is a lack of oxygen, even if the fire gets started, remember from your science book, that fire triangle, where you had, if you have just for your recap, we have a fire triangle. Where the one end is something which can burn, the other end is you need to have ignition source, and then the other thing is you need to have the air supply. So once the fire triangle is complete, then only the fire can propagate. Here, methane being flammable, say if it will catch fire, it will start burning, but and garbage can burn, so we do have things which can burn, but since there is no oxygen, because we have compacted the garbage, there is no oxygen present, and that creates, so the fire will not propagate. So that kind of helps in controlling the fire in a landfill environment. So that's so to do all those calculations, to understand all those factors, you need to know what is the porosity of the garbage, and that's important. And then the other point, say if you want to operate a landfill as a bioreactor landfill, if you're trying to do the air injection into the system, there we need void spaces. If when we do the composting, for example, composting requires we need to inject air, because composting is an oxidation process. It's a aerobic biodegradation kind of stuff. So when you're doing the aerobic system, you need to supply air. And when you are supplying air, the air has to travel in the garbage. So again, if you look at this sketch over there, so if you think about this is a pile of garbage. If we are trying to inject air here, so if we are trying to inject air, the air has to travel, and for the air to travel, more the void space, better it is. So the air can travel and go towards the different parts of the waste, and then your aerobic reactions will be better, things will degrade, you will have a better compost. And to do that, many times what we do, we add certain things which actually increases the porosity. That's called the bulking agents. You will hear the term bulking agents when we go to the compost chapter as well. These bulking agents are used, which is not doing much to the degradation of the garbage, but it is actually helping improve the porosity of the waste mix, and that porosity helps in air movement in our compost pile. So those are the reason why the porosity is important, and that's why porosity is one term which we will be kind of using it quite like we have to use it in a many times you will see the porosity being used in the waste calculation. So that's porosity part. Now there are other physical characteristics: particle size and size distribution. What is the size of the particle? Especially again, if you have remember from your soil mechanics class, those D60, D10, uniformity coefficient. So all those factors comes in picture here too, because we are talking about the stability, we are talking about how the garbage will be compacted. So if there is again, if you have all big particle sizes, so remember we have seen this example before. Say if all of them are uniform size, if all of them are the same size, that means I will have a more and more void spaces. But if I have something smaller pieces in between, and that will that will fill up these void spaces. So that's if I have a uniformly graded soil or uniformly graded waste mix, it's better for compaction. So you will have things kind of, but if all of them are of a similar size, that becomes a problem in terms of having a better compaction or better. You will have lots of void spaces, you will have lots of pore spaces and all that. So that's why particle size is important, particle distribution is important. Particle size is also important when we talk about the waste to energy plant, because uniform the particle size, better it is. Otherwise any process, they like to have uniform feed. So even the coal based thermal power plant, if you visit a coal based thermal power plant, they always want to have coal of a particular size, and that size should not change a lot, because then your reaction efficiency, everything kind of goes a little bit off. So if you have a uniform size, it's always better. So similarly here we have to do that too. Hydraulic conductivity or permeability, it's a term used to measure how the water will flow, at what rate the water can flow. Remember we looked at the liner system, typical liner system, the permeability was less than 10 to the power of -7 centimeter per second. So even in the case the liner breaks, that soil, the clay soil at the bottom of those liners, they will not let the water pass through at the rate of more than 10 to the power of -7 centimeter per second. So that's like a very slow movement of water, and we need that to prevent our groundwater contamination. So those are the terms we are important in terms of the hydraulic conductivity and all that. So these are some examples, particle size distribution. So if you look at different the different samples, 12, 13, 15, 16, and these are unprocessed refuse. So here as it says, it's unprocessed, it has not been processed, it's an unprocessed refuse, and it is coming from one particular book. So here as you can see, basically coming from some research project, as you can see over here, different samples, and on the y-axis you have the percent finer than x, and on your x-axis is the particle size. So and for the different samples there are certain variability. So we do see certain variability in terms of how the particle size are, and that depends on what kind of waste it is, what is the source of waste and all that. So and sorry, and for another, let's look at the other example. So we'll look at like how to calculate if you take a non-spherical particle for which the length is given to us, and length is given to us, and width is given to us, and the height is given to us. We have to calculate the particle diameter by using definition. There are different definitions for particle diameter. You can take one definition is where you take the length itself as a particle diameter. That's one definition. So you can 2d is equal to L is equal to, so let's say 2. Other definition is where you take the width and length together and take an average of that. Other definition of calculating diameter where you take all the three, height, width and length, and take the average of that as well. You can also take a square root of the area, then you can take a cubic of if you calculate the volume. So basically there are different ways of calculating it, and what we see is that data varies from 1 to 2.2 depending on the definition. So whenever you see a definition what diameter calculated for a non-spherical particle, make sure that you understand how it was calculated. As you can see over here, based on how you go about it, and these approaches are okay. There are people have done these approaches, all these approaches has been used. So you have to understand which approach people have taken, so that you can get the background of how it was calculated. So that's important. So this is another kind of example when you are looking at different properties. Then another areas where we talk about the proximate analysis and the ultimate analysis. Proximate analysis, this is a term used where you are looking at certain parameters such as the moisture. As you can see over here, these are the proximate analysis terms we have, where we look at the moisture, we look at the volatile matter, we looked at the fixed carbon, we looked at non-combustible, higher heat values. So those are, and these are all percent by weight or depending on the, usually the heat value will be kilocalories per kg. So moisture, typical moisture 15 to 35%, volatile matter is 50 to 60%. What is a volatile matter? Volatile matter is the matter like the volatile solids, which you may have already seen in some other courses, but it's essentially if you take a sample and put it in a crucible, put it in muffle furnace at 550 degrees centigrade over a 3 days period, and then you look at what is the mass which has gone. So that mass, the loss of mass is essentially that denotes as the volatile matter present. Fixed carbon is the amount of is a type of carbon which will not really react. Then we have some non-combustible, and then the heat value. So this is known as the proximate analysis. So basically you are getting some idea about the garbage. You are not getting the idea in kind of great detail. When you try to get the idea in great detail, where almost you are taking things all the way to the periodic table level, that is called the next part, which is the ultimate analysis. Here the ultimate analysis part is where you look at the moisture, carbon, hydrogen, oxygen, nitrogen, sulfur, and those are your basically the stuff that you see directly on the periodic table, and you get the values for these. Why this is important? Again, as I've been emphasizing from the very beginning of this course, for anything that you do, make sure you understand the significance of that particular task, or anything that you read, try to understand what is the significance of this particular topic. So again, why this proximate analysis and the ultimate analysis is important from a waste management perspective, how they will be used in waste management perspective. Remember, we were talking about we have to find out how much leachate will be produced. We have to look at how much gas will be produced. So for looking at how much leachate will be produced, moisture content is important, isn't it? We need to know how much is the moisture content, because that is one of the source of the leachate production. How much gas will be produced and what rate the gas will be produced, and how much the waste will eventually degrade For that we need to know the volatile solids or the volatile matter. So there is always, whatever we are learning in a course, there is always some reason for that, and it's better you understand those reasons, and you will feel more excited about it, you will feel more interested in that particular course, and you will not forget the topics quickly, and it will get into your head over a long period of time. So that's for the proximate. Ultimate analysis, going all the way to carbon, hydrogen, oxygen, is it needed? Sometime maybe not, depending on what's the requirement. When it's needed, say if you have to calculate the air requirement for the compost plant, or you are trying to find out how much gas will be produced from an anaerobic digestion or in a landfill. For that we use a formula to predict the gas, how much gas will be produced or how much air will be required. And when we try to use a formula, we need to know the formula of the garbage that we are supplying. So since the garbage is so much heterogeneous, there is we don't know the formula. So for that, if we know the amount of carbon, hydrogen and oxygen percentage wise or the mass wise, by doing this ultimate analysis, we can come up with a chemical formula of that particular waste stream. And you will see that we will do those kind of problems in this particular class. We will not do it today, but definitely at some point of time in coming modules you will see that. So that's the reason why this proximate analysis and ultimate analysis and these things are important. So that's kind of, I hope that kind of clears up some of the concept there. And is tensile strength of the municipal solid waste component. That's another example where can be used, and why it is important. Again, we are using different types of materials. We want to recycle those materials, we want to look at make new things out of these materials, and there are other applications. We are going to compact these materials as well. So for that, here if you look at a typical stress strain curve, which usually you will see in a like a structural engineering class or strength of mechanics, those kind of class. So here as usual we put the y-axis as the stress and the x-axis as strain. Both y and x-axis is in the log scale, and as you can see from here, we see there's, of course, there is a linear term, and then we have like a non-linear stuff in there. And for the linear term, stress is proportional to strain, as we know, and the ratio of that is called Young's modulus. And but as we go to the non-linear term, things are a bit different, where we have some of the failure points are clearly defined. Some places we can see some plastic behavior. So those things are given. And typically we follow a test specimen, what is called as test coupon. There is a standard way of doing it. So and that what is the text coupon we have used is kind of given over here. So for different this is kind of a standardized now. So for different even for different waste streams, different type of waste, we always try to use this particular test coupon so that we can compare the results. So that's it's like important from that point of view. So far we have looked at the waste stream by itself. We have been looking at the waste stream just by itself. We haven't looked at if there are certain, usually what will happen is, say if you are running a landfill, or if you are running an anaerobic digestion plant or a compost plant or a waste to energy plant, you will not have the garbage just coming from one particular location. You will have the garbage coming from variety of locations. So you will have waste coming in. So if you know the individual waste stream properties, how to find a combined waste stream property? Again, it's a simple math, weighted average kind of problems. So let's look at some examples just to make things clear for you. So how you determine average property of the mixed waste stream? You can do it. You can do this average moisture content, as you can see here. So what we are looking at here, we on the top we have all the moistures from different waste stream. So moisture content from the waste I multiplied by the mass of total mass of I. That's what it is giving us. It is giving us the amount of water coming from the individual waste stream. And what is there in the bottom? Bottom is the total mass. So as we know, the moisture content is what? Total amount of water present divided by the total mass. So that's kind of gives us the moisture content. So same thing has been done over here. This is nothing kind kind of a rocket science on this particular aspect. So if you look at one example where you have the residential waste has the following components: paper is this much, glass this, food this, yard waste this much, and if you have to estimate the moisture content using the typical values which is provided in the table over here. So these are my these are my different waste components. I have these are my waste components. Let me get that. These are my waste component. This is the typical moisture content. So one way we can do is since we know that the moisture content, we can calculate what is the dry weight based on 100 kg, sorry. So if 6% is the moisture, 50% is the paper, so out of based on 100 kilogram of the total weight, we'll have around 47 kilogram of dry paper. Similarly for your glass, and similarly for food waste and yard waste. So that's, if you know that, we can calculate. So if 76 out of 100 kg, 76 kg is dry, so that means 24 kg is the moisture. So the moisture content, since we are working with the 100 kg, moisture content becomes 24%. So same thing has been done over here, where you can see that it's a W minus D divided by W. So W is weight is total is 100, 76 is the dry, divided by 100, and then you multiply it by 100 to get the percent. So it's around 24%. So that's the amount of like a moisture content for this particular waste stream. So average density is what? Density is mass upon volume. So we have to density, again, we cannot take a weighted average of density. The question is why, and try to understand that why I am telling that, because density is not an independent parameter. Density is a dependent parameter. Now when I say independent parameter and a dependent parameter, what does that mean? Dependent parameter means density depends on both mass as well as volume. Mass by itself is an independent parameter, volume by itself is an independent parameter, but density depends on both mass upon volume. So that's why it's when we do the average density, we cannot just take the weighted average, because the mass, and when we mix two things together, the volume will change and so is the mass, and they may not change in a certain ratio. So we have to look at them in a separate way. So in terms of the average density, what we do is we take the total mass on top. So as you can see over here, we take the total mass on top and then we take the total volume. So that's the density is mass upon volume. So we take the total mass on top divided by the total volume. Now what the total for the total volume, how we will do it? Volume is if you remember, density was mass upon volume. So we can, so that means volume is equal to mass upon density. So that's what you see over here at the bottom. So mass upon density for each one of the waste components, and summation of that gives us the total volume, and on top we get the total volume of the moisture present. So total volume of moisture divided by the total volume gives us the we get the total volume of here, we get the total volume here, and we get the total mass on top. So as we know, mass upon volume gives us the density. So that's how you can calculate average density. So those are pretty simple but straightforward stuff. So that's how you can do in terms of like an average of two different waste stream. Now we will start looking at, so we have kind of in terms of the physical properties. If you remember from the previous module, we were talking about that we'll look at the physical property, we'll look at the chemical property, we'll look at the component composition. So with that particular, with this particular slide that we just finished, we kind of finished the part of the physical property. Of course, we will have several math problem for you to work on, and there will be some assignments as usual it happens in this kind of course. So we'll have the assignments and other things coming in as well. But in terms of component composition, we'll start looking at since we finish the physical part, we'll start looking at from the chemical perspective. Now what is the composition of the waste, or also from the component, like what are the different waste streams present in a typical MSW waste, municipal solid waste. So composition of the waste by different identifiable waste components. So what we are talking about here, let's look at some examples that will make it clear. So if you look at the MSW generation rate, it is tons, like a per capita generation has kind of, and again this is the US EPA data. From an Indian data, unfortunately we would like to have some data like that. That would be really cool to have a data, and to collect this we should start kind of collecting data now, so that maybe after 30 some years we can have some nice graphs like this, what we see in front of us. So here historically, based on the data collected in the United States, what they have seen that that's orange dotted line and the orange boxes are for per capita generation in the household, and the triangles are total waste generation in million tons. So if you look at that orange one, we see that there was a trend of waste generation going up, but now there is a tendency of waste generation either coming down a little bit, and for that we don't know what is the reason. So of course it's maybe more awareness, people are more aware now because of all the things that gets highlighted in different media, and so that could be the reason why people are becoming a little bit more less wasteful, and probably recycling and doing those kind of things a little bit more. But this will be informal recycling, because here MSW generation rate means whatever is the waste going into the dumpsters, and that includes the recycling can as well. So but that could be one reason people are being less wasteful. And the other reason is, if you look at over the last 10-15 years, the type of packaging material and the amount, although the amount of packaging material may have gone up, but the type of packaging material and the weight of those packaging material, this is all based on million tons, so it is based on the weight. So the weight of the packaging material is actually, we see that weight of the packaging material is going down. So since the weight of the packaging material going down, ultimately the overall weight will go down. So that could be some of the impact over here is because of those kind of things happening over there. Same thing over here as well. So and then overall, like if a cumulative is what you're seeing in the green line with the green triangles, and you see that the waste has been increasing, but it's kind of decreased a little bit in the last decade. So that's kind of gives you some examples along in terms of the MSW generation rate. So being said that, then we have different types of in terms of the waste composition, like different pie charts are out there. We'll look at how these pie charts are produced. But as you can see, typically, again, this is from the United States, from the US EPA, the paper seems to be a very high component of the garbage, and this paper is essentially office paper, and those are the kind of paper, newspaper, office paper, those are the kind of papers which you will see. There are some food scraps, some yard trimmings, wood, rubber, textile, plastics, metals, and glass. So these are and some of those kind of MSW generation by material in US. So, but how these pie charts are developed? So how this, and we'll talk about that. How we get this kind of pie chart? Say if I want to get a pie chart made for a particular town, how I can go about and do it? So that's kind of important in terms of looking at these pie charts. So let's look at how this is. So this is another example, same thing in 2009, nothing much difference here. And USA 2006, this is before recycling in terms of the different categories, container and packaging, non-durable goods, durable goods, food scraps, yard trimmings. So this is in million tons, it's before recycling. Then this is again before recycling. You see a lot of material that is going into the waste stream, and this but how we get those pie charts, because those pie charts are very, very important. Say if I have to know what kind of garbage I'm getting in, and based on those pie charts I can make a decision whether I should go for a waste to energy plant or go for biomethanation, or whether I go for landfill and what not. So but that pie chart is important to give us an idea about how the waste, how the waste is generated. So how we do that? There are two approaches we use. One is called source specific approach, the other one is called the material flows methodology. So what is the source specific? We'll look at the material flow first, and then we'll go to the source specific. So material flow approach is essentially you do a mass balance. You look at all the mass of material entering the waste stream. So estimated from the amount of, and how we estimate that based on how much of that material got sold off, what was its shelf life or the useful life, and then assuming that in that useful life this material will come into the waste stream. Say if you look at an example, say laptop for example. So you bought a laptop, and for a typical laptop of that particular type, a typical age is say 3 years or 4 years. So after whatever you bought it this year, after 4 years we'll start considering it as a part of the electronic waste stream. So that's one way of doing it. That's called material flow methodology. So where you look at the amount of material that is going around. So it's so there is you can estimate the amount of materials predicted to be discarded on the amount of the material produced. In other words, a certain number of aluminum beverage containers are produced every year in US. These products have a very certain lifespan before they enter the waste stream. Once they enter the waste stream, we can based on their lifespan, based on how much they are produced, we can calculate whether it will enter the waste stream or at what particular time. So the magnitude of the waste can be estimated by the production statistics. Of course, there is a drawbacks to that. Source specific approach, as you can see on this picture here, where myself and some of my students and other people we are trying to do a waste audit. We call this a waste audit, and where we are taking the garbage. As you can see over here, we are taking it apart. After taking the garbage stuff, we are taking it apart, and then we are collecting it into different bins and weighing those bins, and then we are collecting the weight. That's myself taking the data over there. So this is myself, and with some of our other colleagues and other students, we had to try to do that like a waste composition study. So this was kind of interesting. So that was that's another approach that you can use. And so let's stop here, and we'll look at another example of how the waste audit was done in one of my class earlier. So again, that will be pretty quick. And so let's stop, and then again, so what we have done in this module, we started with the porosity, we started with looking at the moisture content, looking at porosity, moisture content, and we looked at how if you have the two different waste streams, if they mix together, how to calculate their average properties. Then we also looked at that in terms of the component composition, how the waste pie charts are developed, how these pie charts are made, and at the same time there are two approaches, the source specific approach and the material flows methodology. We talked about the material flow methodology. Regarding that source specific approach, we saw a couple of slides, and then we'll see some more in the next module. So again, I hope that you are enjoying this course. If you have any question, feel free to post it on the discussion board. We'll be happy to answer. We are keeping an eye on discussion board. Our usual, we try to have a turnaround time of around less than 24 hours there. Okay, so thank you, and keep enjoying this course.